Hi, I'm Xinwei from John Simon's group, the same subgroup as Abhishek, and today I'm going to talk about our kind of the side project, but our newly developed 10 megahertz spatial light modulator, which we see as a promising tool for fast and flexible control in the neutral quantum processes. So, so if we look at the current local addressing solutions, the liquid crystal spatial light modulator and the digital mirror devices can generate arbitrary intensity patterns, but the independent of the control of the of each spot is difficult, primarily because we need to calculate the phase mask using some GS or machine learning algorithms, which does not have a direct pattern to phase mask mapping. And for the cross ALDs, which are widely used today for coherent atom transport, the RF frequency is basically linearly mapped to the positions, which is very easy to control, but we are limited to a grid-like pattern structure. So there are other proposals like the combined SLM plus DMD methods, but it does not quite satisfy our need, which is to have a fast, continuous, and flexible control of our neutral atom processes. So we here propose the RIPA-SLM as a new tool for fast local addressing. So it has a super fast 44 nanoseconds rise and fall time, which is intrinsically limited by the speed of light. And it can generate arbitrary patterns while also having efficient frequency to position mapping. So in short, our scheme uses a high resolution 2D spectrometer to map these frequencies to the positions with a raster scan pattern across the image plane. So we use a fiber electro-optical modulator to generate these optical sidebands, and then which enters these 2D spectrometers. So after the amplification and filtering. Moreover, we can simultaneously generate many optical sidebands. So in this way, we can write a spatial addressing pattern in the frequency domain and onto the image plane. The system is then essentially a frequency encoded monitor. So a problem arises as we try to build it, because the RF and fiber modulator system has only about 20 gigahertz of bandwidth, while the conventional spectrometer has gigahertz scale resolution. So as a result, only a few spots can be resolved. So to address this challenge, we invented a spectrometer reaching an ultra-high megahertz level frequency resolution. So building this spectrometer with megahertz frequency resolution fundamentally requires you a very long path length difference delta L in an interferometric device, which is on the order of 100-meter scale. A typical diffraction grating gives us a delta L of centimeter scale, so it provides a frequency resolution of about 10 gigahertz. And the most dispersive object known to people, which is the virtually imaged phase array, or VIPA, folds kind of a meter scale path length into these repeated reflections between two surfaces. Therefore, it can have a frequency resolution of about 100 megahertz. The incident beam outcouples at each round trip, and with a lens that interfere all these beams, it forms a sharp interference pattern whose position depends on the input light frequency. So the reason we cannot further extend the path length in VIPA is that the divergent incident beam gives non-overlapping spatial mode that would degrade the interference pattern. So we noticed that a lens could refocus the beam. So therefore, the combination of the two result in a new optics, which we call the re-imaging phase array, or RIPA. Here, a single Gaussian beam enters this round trip and circulates within the RIPA structure, in which we have a commercial optics called the microlens array, such that each round trip passes through one of its microlens. The microlens basically re-image the spatial mode onto itself, but up to a round trip displacement to match the microlens array pitch. The propagation will unfold like a lens guide that could stabilize the beam trajectory and also maintain the identical spatial mode. Do you hear any questions? Okay. So during the propagation, the beam acquires a propagation phase shift phi y, which is basically k times L round trip. So the L round trip being the length of each so each round trip path length. So remember, k is 2 pi over lambda, which is 2 pi c. So 2 pi over c times nu. So this k is dependent on laser frequency nu. So after the outcoupling, the resulting 1D phase array will therefore have a phase step phi y between its adjacent beams. And this phase profile looks like a discrete sampling of a tilted planar wavefront. This can be understood because in a planar wavefront, if you look at a constant z cross-sectional phase, the phase profile looks like e I k y theta, sine theta. Y is in this vertical direction, and theta is a tilt of the planar wavefront. So then when you go up by each p, then you have a phase increase of, like, say, kp sine theta. While in the phase array, it's kind of a sampling of this tilted phase array, but it has so it only have a beam at each pitch away, but it has a phase increase of phi y. So if phi y matches this kp sine theta, so then the two is having so roughly the same wavefront structure, which is basically a linearly increasing phase gradient. Okay. So therefore, after a lens, this tilted wavefront will focus to a moved position, and this movement will be frequency dependent because it linearly depends on the wavefront tilting, which linearly depends on phi y, and then linearly depends on the frequency change nu. So by changing this input frequency nu, we can scan the image plane linearly in one of the directions. So with a single RIPA, we broadcast this 0D input into a 1D phase array. And if we cascade this process along the other dimension, we will have a 2D phase array. The actual geometry is shown on the left, while the first RIPA has a round trip length of 9.4 centimeters, and the second RIPA has a round trip length of 2.3 meters, in which we added two 4F telescopes in addition to the micro lens array to extend the path length. So consequently, if we scan the laser frequency, the interference pattern will move much faster on the horizontal direction than on the vertical direction, basically because the second RIPA, which expands the horizontal direction, has much more frequency dispersion compared to the vertical direction. So then the frequency spectrum within 3.2 gigahertz is thus mapped onto the image plane row by row. With this mapping, we want to make some images with the RIPA-SLM. So with a single optical tone, it makes a single diffraction limited spot. While we simultaneously inject 11 independent frequency tones, the RIPA-SLM maps each tone into a distinct spatial location that synthesizes a letter S for Stanford. So these frequency tones are modulated from a carrier frequency with an electro-optical modulator. There will be symmetric plus and minus sidebands, and we employ a second-order Butterworth optical filter to select only the +1 order sidebands before they enter the RIPA-SLM. So basically, you can think about a electro-optic modulator only has phase modulation. And if you want to synthesize any pattern with changing amplitude modulation, you have to have a frequency-dependent component in your optics setup, which is a filter. By modulating these frequency tones, we can demonstrate the dynamic operation of the RIPA-SLM. So we collect data with a scanning photodetector with a 50 megahertz bandwidth. On the left, the pulsing measurement shows a symmetric 44 nanoseconds rise and fall time with a stable intensity profile during this on time, 1 microsecond on time. We also tested frequency sweeping, where two spots translates continuously across the image plane in opposite directions within 200 nanoseconds. So this moving pattern is not available in the conventional crossed ALD systems. Any questions to here? Okay, so let's take a step back and ask why it works. A key concept underlying the operation of our spatial light modulator is the phased array, which consists of an ensemble of coherent light beams with ordered spatial positions and well-defined phase relationship between them. So if the adjacent beam has a phase difference phi x and phi y in the x and y directions, then the combined field arising from their interference has a propagation tilt along x and y, which is proportional to phi x and phi y. Intuitively, this looks like a bunch of low NA beamlets combines to give a large beam with a wavefront very similar to a tilted plane wave and can focus to give a high NA interference pattern. At a physical level, local addressing is simply a wavefront engineering problem, since a linear phase gradient basically Fourier transform to a displaced addressing spot in the image plane. So in principle, if we want to synthesize multiple spots, this will correspond to a sum of different complex linear phase gradient, right? So each phase mask is mapped to one spot. This sum of linear phase gradient is a general complex optical field containing both amplitude and phase modulation. However, conventional approaches complicate this story, either because its actuator cannot represent a general complex optical field, such as in the SLM and DMDs. They can either provide amplitude modulation or phase modulation, but not both. Or because the geometry itself imposes a limitation, as in the crossed ALDs, the output field can be written as a product of the two modulation functions on both axes. Therefore, the output has this outer product grid structure. The RIPA-SLM is conceptually different. Here, the addressing pattern is encoded in the frequency domain. The optical propagation in round trips engineers the required wavefronts and decodes these frequency tones into phased arrays, which are superimposed in different frequency channels without crosstalk. And after the Fourier transform, each phase array has a one-to-one mapping back to the spatial location, and therefore each spot can be independently turned on and turned off because each spot is correspond to a single frequency tone. So you just synthesize a wavefront which turns on a frequency tone, and therefore there will be one more spot on your image plane. And they can also be modulated in amplitude or phase, because you can basically map the amplitude and phase of your frequency tones back to the spot. So to make the RIPA-SLM actually useful and scalable, we have some technical limitations to address. The first is the power handling of our device. So a typical high bandwidth waveguide-based electro-optic modulator can handle a few tens of milliwatt of optical power. But we can boost its optical power afterwards. We basically inject this spatially single mode but frequency-wise multi-mode output of my modulator into a high-power optical amplifier. After that, the system is entirely based on free space optics, which according to our calculation could handle up to 30 watts of optical power. And moreover, we can also do wavelength conversion, where the wavelengths that are not directly modulatable by an ELM, such as UV and other frequencies, could be generated by a single mode some frequency or difference frequency generation in nonlinear crystal. So and our modulator could operate in telecom bandwidths. So because the total spectral bandwidth of this spatial light modulator is only 3.2 gigahertz, so neither the gain profile of the optical amplifier or nor the phase matching condition in this nonlinear crystal will be a limiting factor. Our phase array consists of a bunch of beams coming from the circulating round trips, and any path length variation and optical imperfections will shift their relative phase, and therefore will heavily degrade the interference pattern. To address this, we apply a static SLM phase compensation mask after the generation of the 2D phase array and before the imaging to compensate for these potential residual phase shifts. The phase mask is calibrated using these standard interferometric methods, which is to interfere these beamlets within the 2D phase array with a reference beam, and then extracting these this residual phase from their interference fringes. Ideally, when a calibrated phase mask is applied to compensate these residual phase, these fringes will overlap and they will interfere constructively to give a peak at the center. So this is experimentally what a calibrated phase mask looks like. It is not like the standard Zernike polynomials that we use to describe the astigmatism in our imaging system, but rather it is an accumulation of our path length drifts and the length astigmatisms in different round trips than mod 2 pi. And this static phase mask, once calibrated for a specific wavelength, can work for all wavelengths within our operation bandwidth. The first reason is that the phase array is static because because it occupies a single optical input mode. As the input frequency change, the mode doesn't change its spatial locations. So all of these path length drifts and the aberration on length is basically the same as our frequency change. The second reason is that because the RIPA round trip itself has much more the dispersion compared to the other components in the device, such as our lens, our SLMs, etc. So these components has essentially no dispersion within the gigahertz scale frequency span. So therefore, this calibrated phase mask can work for all wavelengths. One might also worry that the mechanical noise could shake our mirrors and causes the path length to drift. So especially since we are working with meter-long round trips. Luckily, this mechanical noise mostly appear as common mode fluctuations in the path length, which translates the interference pattern without degrading it. So we can actively suppress this shaking using a single piezo translated mirror. Finally, I want to discuss how to build a neutral atom quantum processors around the RIPA-SLM. So the RIPA-SLM provides scalable control of neutral atom processors. It supports local addressing of a selected set of atom qubits for single qubit rotations through these dispersive light shifts or Raman transitions. It can also generate reconfigurable moving tweezers for coherent atom transport. So these Gaussian-like moving tweezers moves continuously along the grid lines and can hand off their atoms at their intersections and perform arbitrary atom routing with asynchronous scheduling for all of them. The high speed of RIPA reduces lensing effect, while the frequency variation across the image plane suppress low frequency intermodulation that could cause the atom heating or loss. For an outlook, we have a concrete plan to scale up RIPA to 80 by 80 and beyond, while also shrinking its footprint within 10 centimeter scale. Moreover, the arbitrary routing pattern that the RIPA-SLM provides can enable a lot of moving primitives that accelerate several operations in a neutral atom quantum processor, from the defect-free array assembly to the patch rotation needed in Hadamard gates for surface code, and further to the more complicated rearrangements in these modern magic state cultivation schemes. Across these demonstration problems, RIPA-based movement show us a speed up ranging from 2x to 8x compared with ALD-based movements. Here we assume the acceleration of atoms are the similar for both RIPA and ALDs, and the kind of the 2x to 8x speed up is only arising from the fact that we have better compilation of our moving operations, so it can provide this constant boost up, yeah. And with this, I would like to thank the audience, our lab mates, PI John Simon, and the founding agencies, yeah. And thank you for all listening.
Thanks. It's a very good project. I was wondering, like, have you actually demonstrated the diffraction limited spot generated by the RIPA? This is like the first question, because from what the data you show, it's actually somehow more like couple micron in the beam spot size.
Yeah. So
yeah, and also there's a second question is because the spot is generated by the interference, and you always have like the first order like a ghostly imaging around your unit cell, right? If you look at this spot,
yeah.
And how much that affect, because I think it will play a big role for your rearrangement or local addressing in your case. So that's my two questions.
Yeah, so these are two great, great questions. So why I say this spot is diffraction limited. Basically, if you calculate the transverse, transversely occupied area of your 2D phase array is like 1 centimeter by 1 centimeter, and focused by a very long 20 centimeter focus length. So we are intentionally using that for camera-based characterizations. We are not using an objective like high NA focus beam. And we also, in our supplementary, we discuss the focusing of our high NA objective beam. And it is very similar to the conventional based architecture, because you can just think about the phase array as a plane wave. So the idea of the diffraction limited here is we basically calculate how much transversal occupied area of our output, and then with the focal length so that we choose, and we compare with this 14 micron waist, and these exactly matches. So they are diffraction limited. The second question is that so you are talking about we have multiple brilliant zones, or like the replicates of our patterns. So this, on the one hand, yes, will certainly lose some power efficiency by a factor of maybe 7. But we can increase the pitch to waist ratio by using a micro-lens telescope right after these focusing beams to make the beam more like continuous plane waves. So such that the basically then the replicated power will be lower, and then we can have more power utilization efficiency within our first brilliant zone. And so you're also thinking about, so if this is working with the neutral atom processors, how do I block these other replicates? Well, we can just have a full F imaging and filter at that imaging plane, have a knife edge to cut out all of these replicates, and then full F relay to the actual the objective that you want to use with an atom array.
Thank you. But for your first answer, I think it may be different, because if you're trying to focus down to much smaller ways, then all the aberration comes into play, and it's now like because you have such a long path for your reply, and there's definitely aberration comes from your optical elements, and how do you like? No,
so this is a key concept of this. The RIPA phase array is a bunch of low NA beams, and the NA that the actual focus interference is something this, divided by yeah, so the NA of this is proportional to the transverse size of this phase array, which is not the NA as each small beamlets. So you can change your focal length, but without changing the properties of this phase array. Yeah.
Thanks.
Any other questions? Okay. So if no other questions.